Today we're going to go over the power rule and the proof of the power rule and how to use it. So power rule states that given a function f of x is equal to x to the n, then the derivative of that function f prime of x is equal to n times x to the power of n minus 1. Now this rule is very useful in solving functions, in finding the derivative of functions where the function is set up like this, x to the n. So given an example function like fx is equal to 3x to the fourth. Now instead of plugging this in to the definition of the derivative and solving, that would be very tedious, we can apply power rule. So in this case, f prime of x is equal to 4 times 3 times x to the power of 4 minus 1. Here we're treating 4 as n, so n goes to the front, and then it's just 4 minus 1. And we have this extra 3 as a coefficient, so we have to multiply that. And this equals 12x to the 3. So this is a simple case where power rule is useful. But how do we go about proving it? Well, first to do that, we need to find the derivative of the natural logarithm, y equals ln x. We need to do this in order to prove the power rule, and why I'll tell you later, but first let's just do it. So all ln x, the natural logarithm, is just another way of writing log base e to the x. And this is another way of writing e to the y is equal to x. This is the same as this, since logarithms are just a different way of writing exponents. So in the exponent form, it'd be e to the y equals x. And from here, we can differentiate both sides with respect to x. So doing that, we would get d by dx of e to the y equals d by dx of x. And this would equal e to the y, since we know that the derivative of e to the x is just e to the x itself. So here we get d by dx e to the y is equal to e to the y times dy by dx, since we're differentiating with respect to x and not y. And this, the right side, is simply just 1. The derivative of x is 1. So now we have e to the y times dy by dx is equal to 1. And then we can divide both sides by e to the y. So we get dy by dx is equal to 1 over e to the y. So we're isolating dy by dx, and this gives us the derivative. But all y is here is just ln x, is equal to ln x. So we can plug ln x back into this equation. So we get y dy by dx is equal to 1 over e to the ln x, which is equal to 1 over e to the log e to the x. Now this is simplified, and this will give us just x. So further simplifying, we'll get 1 over x. So we have now found that the derivative of ln x, we have y equals ln x, then y prime equals 1 over x. So this is the derivative of the natural logarithm, and we can use this to prove the power rule. Now that we've shown that if y equals ln x, then y prime, the derivative of y, or ln x, is equal to 1 over x. And we can use this fact to actually prove the power rule. So how would we go about proving the power rule from y equals x to the n? And we have to get, finally, to nx to the n minus 1 equals y prime. Well, first, we would take ln y equals ln x to the n. We would take the natural logarithm of both sides. Now this just equals n ln x. And then we differentiate both sides with respect to x. So on the left side, we just have a case of chain rule. We get y prime over y, and this is equal to the derivative of this, where we get n over x, because the derivative of ln x is just 1 over x. So n times 1 over x is n over x. Now that we have y prime over y equals n over x, we can multiply both sides by y. Y prime equals n over x times y. But we can now here have y equals x to the n. So we can substitute x to the n for y. So we get y prime is equal to n over x times x to the n. Now, we can just simplify this, and if you simplify, you see that we get nx to the n minus 1. So this, we have shown that from y equals x to the n, we have proven, and this is called logarithmic differentiation, we have proven that if y equals x to the n, then y prime equals nx to the n minus 1. And note, this is only for real numbers. This proof is only for real numbers. So the power rule can only be used for real numbers if you're proving it this way.